Hello and welcome to this 8th video in our lecture on hash-based cryptographic primitives. In this video, we're going to discuss the details of the HMAC algorithm. So assume we want to authenticate a message M. HMAC is going to use a block-based hash function, so we're going to break up the message M into blocks. Let's call those Y0, Y1, dot 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 all the way to YL minus 1. So we have L blocks. Each block is exactly of length B in bits. So we have a B bit block. Okay, then we going to pick a black box hash function H that is going to take a message of any length and hash it to a message digest of a fixed length, say n bits. So this is the output of the hash function. Okay. Now we're also going to have a special bit string called the input pad, and that will be a piece of data of length B. And we're also going to have another bit string called output pad, also of length B. So this is the input pad and the output pad, and these are not drawn to scale, but these are B bits long. And the content of the input pad is going to be the X digits 3, 6 repeated. However, a number of times you need to fill up B bits, and then the output pad is going to be the X digits 5C repeated to fill up the pad. So these are the main components of the HMAC algorithm. Let's not forget that we also have a key which is required. It's a shared key between the sender and the receiver. So this key is also going to be a bit string. Now, because we're going to do an XOR between the key and each one of these input and output pads, we have to make sure that the key, whose length could be anything, actually has a length equal to B bits. So we need to modify this key by either padding it with zeros to make it long enough, namely equal to B bits, or if it happens to be longer than B bits, we could hash it using the hash function H, and so you can bring it down to B bits. Eventually, we end up with a new variation of the key that we're going to call K plus. So the HMAC algorithm, whose formula is given over here, is actually going to use this new modified key that has exactly B bits in it. So the formula for HMAC is as follows. We're going to start with the input pad. We're going to XOR it with that key. We're going to prepend the result to the message M, and we're going to hash that. So this gives us a message digest of size N. We may have to pad this up to B bits again, and then we're going to concatenate it with whatever we get by XORing the key with the output pad, and the result of this concatenation will be hashed again. And the output of this hashing step will be the MAC code. So we're going to unpack this formula by visualizing it in a diagram and going through the steps again one by one. So here is a visualization of this formula. So in step 1, we're going to transform key K into a key K plus, as we explained before, using some padding, for example. Once we have K plus, we're going to XOR it with the input pad. We're going to call the result the block B bit block SI. for the input S block, we're going to, in step 3, append this block or prepend it in front of the message M, which itself is broken up into blocks as we talked about before. So now we have a new message M prime with a preliminary block inserted in front. We're going to hash that using some initialization vector of the appropriate size. Then we're going to take the same K plus we used up here and we're going to XOR it with the output pad. This will give us a new block of size B called SO for the output S block. So we're going to grab the message digest obtained here from step 4. We're going to potentially pad it up to B bits. So now we have 2 blocks that we concatenate together. And finally, we apply the hash function again with some initialization vector to get the final output of the HMAC algorithm. So this is the complete detail of the HMAC algorithm. And one thing to notice is what we're doing basically with the K is we are producing from K plus 2 different keys. Okay, we're producing the key SI and the key SO. And notice the way we produce these keys is by XORing the original K plus with a different bit pattern. So for example, remember that when we talked about the input pad, we said the value would be 363636. So if you remember, the binary representation of 36 is going to be 0011 for 3 and then 0110 for 6. So we're going to repeat this pattern a bunch of times and then we're going to XOR that with the bits of K plus. Now remember that when we XOR something with the bit 0, it remains unchanged, and when we XOR it with the bit 1, it flips. So by using this XOR operation between the input pad and K plus, we end up flipping a fraction of the bits of K plus to get some new key. And then when we do the same with the other pad, the output pad right here, whose values are 5C, 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 we end up doing the same thing, but with a different bit pattern. So 5 in binary is 4 plus 1. C is 12. So it's this bit pattern. We end up XORing this with the bits of K plus, and we get a different subkey, if you wish. And notice that because the bits here that are ones are different from these ones, we end up pseudo-randomly generating 2 different subkeys starting from the same key, K plus. So make sure you understand this picture of the algorithm for HMAC and also remember the corresponding formula for it. And this concludes our discussion of the algorithmic details of HMAC.